We learned last unit that like sometimes you want to accumulate, oh man, you just use geometry and you get the exact answer. Like I just have a triangle. Base of 2, height of 5, we're good. But if you don't have geometry, and you want to find an accumulation, how do you find it? And if you don't have a calculator, don't say I use a calculator. If you want to find the accumulation of x squared and you don't have a calculator, how do you find it? Tell your neighbors. Yo, you guys are so much better in first period. You're correct. You have to take the antiderivative. And you're like, but I get a plus c. Well, you don't care. You don't care. We're going to start using this a little bit more, okay? Where it's like, I don't really know what x squared is. Is it a derivative? Is it f? Is it a second? Like, who cares? It's just like, I want to accumulate that. I want to use this antiderivative. You could think this is f prime. You could use f. The displacement of f tells you the accumulation of f prime. It's the whole beautiful sign analysis extra layer where if you like have f prime, you know f is increasing. The accumulation of the derivative tells you how much you increase. You can find this using your calculator, hip hip hooray, or you can find your ending position, subtract your starting position, f of b minus f of b. F of b minus f of a. F of b minus f of a is the accumulation of f prime, right? So this is just going to give you 8/3. Cool. So we keep this in mind that we like getting exact answers. And we could use geometry to get an exact answer. We could use antiderivatives to get the exact answer. But what if we encounter an integral, and we don't have our calculator, where we're pretty sure it's not going to be like a bunch of straight lines, so we can't get our answer using geometry. I have no idea what the antiderivative of this is. So I'm just kind of like in a question mark scenario. Like, I don't know what this will equal. Here's another situation. What if I just say, hey, accumulate f from 0 to 9, but you are just given a limited amount of information about f. These are 1, 2, 3, 4, 5 points on f. Now, what's very important is you don't know how to connect these points. You're like, oh, yeah, I could just use geometry and kind of like turn this in. You don't know that. F could like go up and down a whole bunch connecting these points. So like we can't assume anything. What we can do in these scenarios is approximate. Maybe don't worry about equals. Maybe instead of equals, we think, what is my area approximately? What is my accumulation approximately? So here is a random function. We'll call it a random f of x. We're going from 0 to 1, 2, 3, 4, 5. And I'm going to ask you, hey, you don't have the equation for f that creates this graph. You don't have it. You don't know what the antiderivative is going to be. Like if you use big F, it's like, well, that doesn't really help me because I don't know what it is. So what we can do is approximate this accumulation, approximate this area. Okay? Give me an approximation. Go. Like, figure it out. What's your approximation? What would you do to approximate the accumulation of F? No, give me a good number. I want a good, give me a good specific number. Don't just like, that's a pretty good number. Yeah. No, but give me a good number. What would you do to approximate this? Give it a shot. Do something mathematical. I like what you're doing. Got 6.5, good one. All right, what else you got? What do you guys get? on, like what? Approximate the accumulation of f from 0 to 3. That's f. What are you doing to get 2?
Like adding.
So you're doing like 3 minus 2?
Yeah, and then like +1.
Does that make plus 1? What does an accumulation look like visually? Right.
Okay, but like.
Well, what do you do? So here's the deal, guys. There's no correct answer here. We're just going to do our best. But what are you all doing? You're all thinking about area. And you're all thinking kind of like how we thought last unit. However, last unit, over the last 2 days, we got exact answers. What you guys are doing is you're thinking, this rectangle, which is like 8, that's probably a little bit more. So maybe you're like, maybe I want to put 7 there. I saw some people do that. Some people are like, oh, this is like -4. And that's close enough, so I'll keep the -4. And then some people are like, this is like a half. And I got a bunch of different answers. But you're all doing it the same kind of idea, which is like, hey, let's just use geometry like we used last unit. Only we're not going to get an exact answer because we don't have straight lines. Instead, we're like, 3.5. Some people are like 6. Fine, I don't care. Some people are like 4. Sure, like cool. But we all do the same thing. We use geometry. Now, something that's not great in a math class is everybody getting different answers, okay? It'd be nice if we all could get the same approximation. And if we all use the same process to get the same approximation. And in comes our best bud. He's like the sidekick to Isaac Newton, Bernard Riemann. And Bernard Riemann creates a Riemann sum. Don't do that today. I'm recording it. And a Riemann sum is just a formulaic way to use geometry to approximate area. We will all get the same approximation because we will all be doing the same Riemann sum type geometric process. Unfortunately, Riemann couldn't make up his mind. And he's like, well, I kind of like these shapes, but I kind of see these shapes, which are similar to these shapes, also working. And he's like, you know what? I'm not going to just make one Riemann sum. I'm going to have 4. There are 4 types of Riemann sums, 4 different types of formulaic area approximations that Riemann kind of invented. 3 of them use rectangles. Oh, rectangles are easy. The left, right, and the midpoint uses rectangles. The last one, trapezoidal Riemann sum, a trapezoid Riemann sum, uses trapezoid, so that's obvious. But again, we're just going to use geometry to not get the exact area, because we talk about curves, to approximate the area. Okay? Here we go. We'll start with a left Riemann sum. All right, so here's the scenario. I'm asking you, right here, to approximate this integral, approximate this accumulation. Just stay with me, we're good. Using a left Riemann sum. Okay, so they will be specific which type of Riemann sum you're going to use. We're going to approximate using a left Riemann sum. Yo. Bro. Are you cool? Yeah, what's up? Who? Yes. You could have asked me on the way in. Sorry for interrupting. Yeah, sorry for interrupting. Can I get a Miss Cone really quickly? Yeah, when you go to the next classroom, just like knock on the door and say, excuse me. You too, bro. That's your boy, huh? And a left Riemann sum uses rectangles. Okay. Now, we are going to approximate this integral. We're going to use rectangles. We are going to approximate the accumulation using geometry. You're using areas. What is the area formula of a rectangle? Cool. Base times height. Super simple. Riemann says, let's let our bases be kind of like x lengths, which makes sense if we're talking about like a graph with x's and y's. We're going to say our bases are x lengths. We're going to say our height are y, but we're going to be very specific about our y's. We're going to talk about y's on the left of our bases. Cool? So, we said approximate the integral using a left Riemann sum with subintervals indicated by the data. Subintervals references like the bases, okay? Indicated by the data means like use as many bases as we can, use as many subintervals as we can. What does this look like? Well, we're going to say our first base will be from 0 to 2. And you can visualize this on your graph of f of x from 0 to 2. What is that base length? That base length is a base length of 2. What is the height that we're going to use? Well, we're going to use the y value on the left of our base. So I'm going to use this y value of 1 as the y value, the height of my rectangle over this base. And you can see this is a rectangle of area 2. You just did 2 times 1. Cool? Let me do one more and see if you guys can go the rest. The next base will be from 2 to 3. From 2 to 3, there's my next base. It's a length of 1. However, using a left Riemann sum, instead of just arbitrarily choosing a height, I will formulaically choose a height of 3. So this y value of 3 I'm going to use as the height over the space. Cool. Could you guys do the rest? And what I did was a base of 1 and a height of 3. 1 times 3. Keep going. You good?
You don't use the 4.
Yeah, you use it.
You have a light.
Feels very inaccurate.
Oh, great statement. All read. However,
So we're missing a triangle.
we're going to talk about what you just said.
What sounds more at all about this?
I am finding the area of these triangles, Anderson. My next triangle is going to go from 3 all the way to 7. And I'm going to, my next rectangle will use the y value of -2 over that base. 4 times -2 is -8. And my last rectangle will go from 7 to 9, but we'll use the y coordinate on the leftmost point of my base. We'll use the y coordinate of 5, and I get 10. All right, so what did we all get for our approximation? We all get 7. We all get the same approximation because we all use the same process. Now the question is this going to be accurate? You have no idea. You have no idea whether it's accurate or not. You don't know how these points are connected. It might be connected just like this. It might be like, oh, I'm going to stick around here, then cup up, and then pop down and stay down here, and then pop. You have no idea. It doesn't matter. Riemann doesn't care. Riemann cares that we got the same answer because we use the same process. Okay? Is that cool? All right. Now, moving on to the right Riemann sum. Allie Anderson asked the question, what happened to the 4? Why didn't we use the 4? Because Riemann didn't want to use the 4. The 4 was just like an extra point, which we didn't want to use because we wanted to use the y's on the left of every base. But now we look for our right Riemann sum, which again is using rectangles. Rectangles' areas are base times height. The base is going to still be an x distance. The height's going to still be a y distance, only it's going to be the y on the right, or over the right of your base. I like to say over maybe instead of on. Cool. So it's the same process. It's going to be the same deal. You're going to be like told, hey, approximate this accumulation, this integral, using a right Riemann sum. We'll use RRS for short. We'll use LRS for short for left Riemann sum, with subintervals indicated by the data. We will all get the same approximation because we're all using the same process. We are going to do bases times height on the right. Got it? Don't copy down what somebody already put down. That's not learning. Thank you, Mr. Ryder. I would have said this. Okay, go. What's everybody's right Riemann sum approximation? Base of 2, height of 3. I got a 6. 2 times 3. Base of 1, height of -2. I got a -2. Base of 4, height of 5. I got a 20. Base of 2, height of 4. I got an 8. Cool. So we got 24 plus 8, which is 32. Great. Is it accurate? I don't know. I don't care. I just care that we all got the same thing. Great. Yes, Verma. So, Verma, right now it's not about accuracy. Verma, right now it's all about getting the same answer. What it will be soon in this lesson is how can we be more accurate? But we're not there yet. Cool. All right. The next process is a midpoint Riemann sum. Hold the phone. I'm changing up the accumulation. Now I'm finding the accumulation of G. And all of a sudden I got a bunch more points. Okay, we're going from 0 to 8, and I got a bunch of points in between. And I'm going to read what's my prompt. Approximate the integral of the accumulation using a midpoint Riemann sum with 4 subintervals of equal length over the interval. Okay, now, pause. The previous 2 asked for subintervals indicated by the data, and we just found as many as possible. So we went from 0 to 1, we'd go from 1 to 2 to. But they're telling us to use 4 subintervals. Now, another word for subintervals would be like what? Tell your neighbors. What's another word for like subinterval? Yeah, like sections, bases, objects, all the same idea. Objections, objects. Okay. So, sections, bases, objects. Yeah, I don't even have to write down. Whatever you guys are thinking about subintervals, you're good. Okay, so if I go from 0 to 1 and 1 to 2 and 2 to 3 and 3 to 4 and 5 and 4 to 5, I'd have 8 total objects. I don't want that. You're told just 4. So what do your bases look like if you're asked to only have 4? Tell your neighbors. Well, you got to start with 0. You're going to have to end at 8. So yeah, the endpoints need to be included, as always. Yeah, since we need 4 objects over an interval of 8, we take that interval of 8, we divide it by 4, and we realize each base has got to be 2. So 0 to 2 is the base of one of these objects. Okay, cool. Now, great. That's the first thing to understand. Now, midpoint Riemann sum is still rectangle. It's still base times height. Heads up, I'm going to put a little star next to this delta x. Don't assume it's going to be just like from one x to the next x. Pay attention. And the height is our y value in the middle of your interval. In the middle of your base. Okay? So, from 0 to 2, oh, I have the y value in the middle of my base of 2. My first rectangle is not from 0 to 1, but 0 to 2. And I will use the y value in the middle as the height over that base. And this first rectangle, base 2 height is 2, is 4. Okay, keep going. Well, your height is 0. So your rectangle is just a flat line, you know? No, who is that guy? No. I did not know him. And he's just walking into the classroom like, you know. Bro. Yeah, that was fine. She was fine. She asked me. And I was like, yes. He goes over to a football player, bro. So, yeah, bro. You know you play football. Okay, great. All right. So he doesn't even know you. Oh, even better. All right. So here, it's like, what about the 0? Listen, Riemann doesn't care. Riemann said, do this, and you did this. That's funny. All right. So we all got the same approximation, not an equals. I didn't mean to write equals, an approximation. We all got the same value. Okay, cool. Could you find a midpoint Riemann sum for this set of data? Just take a guess. Think. Could you find a midpoint Riemann sum for this set of data? Not really think, but just like take a guess, you know? So, you might think, well, can we go from 0 to 3? You could, however, 2 is not smack dab in the middle. 1.5 is in the middle of 0 and 3. So no, that's bad. Can't do that. The next thing you're probably thinking is like, well, if I go from 0 to 2, can I just use like the number in the middle? You don't know that. You don't know what the y value is at 1. You don't know that you connect 2 points with a straight line. You don't know this. So it turns out the answer is no, you can't. You do not have the information that you need to get the answer. You do not have the y's in the middle of intervals to use a midpoint Riemann sum. Cool? Okay. To our last one, the trapezoidal Riemann sum. Guess what? It uses trapezoid. Okay, great. Now, how many of you remember the area formula for a trapezoid? Who remembers the area formula of a trapezoid?
1/3.
Good guesses. All good guesses. Yeah, you guys like all forget it. It's okay. So this is a base 1. This is a base 2. There is a height, h. The area is 1/2 my height times the sum of my bases. Cool? Yeah, that's not how our trapezoids are going to look. Here's how we create our trapezoids. Ready? Come down here. I hate how it skips.
Why can't we just do like Riemann right and Riemann left and add them together and then divide them by 2?
Okay, just watch.
I think we're right.
Isn't that how you would find the Riemann?
I'm pretty sure we're right. Okay, we will use the base, subintervals, as many subintervals as possible. We're not skipping unless we're told to skip. We are going to use both the y coordinates. What does that look like visually? It looks like, and what we're going to do is go to both the y coordinates and connect them with a straight line. You guys remember all of those triangles on top of rectangles from last unit? They are all trapezoids. There's actually an area formula for a triangle on top of a rectangle. Here is the area formula, right here. But it's like, what are you talking about? That trapezoid does not look like that trapezoid. Well, let's shift things and figure it out. If this is an x, and this is one y, and this is a second y, where does delta x show up with our h's and our b's? Where do our y's show up with our h's and our b's? Tell your neighbors. Ready? It's easy. 1/2 the delta x. The base length is actually the height. The height. The bases are actually the height. You know, we just kind of flip it on its side. So this becomes delta x. After you flip it, this becomes like a y2. This is like a y1. Okay? So, this, Ma said a good thing just now. That would have been a lot more useful last unit. Yes, it would have been. But if we went back, we would have found, oh, you could have just did 1/2 times the 2 times the 1 plus 3. Oh, this is a base length of 2. I just need to add this y and this y, and I get 4. Glad we're focused. I'm glad we're locked in. Glad we're locked in. All right, now, hold on. Skip the 2 in the middle. Why don't you guys draw the trapezoid, draw it first, and then give me the area of the trapezoid from 7 to 9. Skip the ones in the middle, I'll tell you why in a second. It is just 9.
Why don't you just do the triangle? Why don't you do the
Just stop. Just don't. Stop. It's 9 because 1/2 times 2 times 5 plus 4. The 1 after the 2 go away. The 5 plus the 4 is the 9. Stop. Okay. Now, many of you will revert on your questions on your AP exam to rectangle and a triangle when you're given the graph. That's fine. But for this lesson, if you're asked to use a trapezoidal Riemann sum, it's actually quicker to just use the formula than to do any sort of visualization. So the next two trapezoids, it's tough to visualize because our y values are like a positive then a negative. Very tough to visualize. I'm not even going to draw it. So instead, all I'm going to do is the formula. I got a base length of 1. I got a height of 3 and negative 2. I have 1/2 times 1 times 3 plus negative 2. Done. That's the area. Don't have to draw anything. Then the next one from 3 to 7, base length of 4, heights of negative 2 and 5. I have 1/2, base length of 4, heights negative 2 and 5. Add them all together. You get 4, 9, which is 13. This is 6, which is 19. This is 1/2, so it's 19 1/2. Is it accurate? I don't know. I don't care. I just care that we all got the same answer. Okay? Okay, great. Okay, back to this question, which was on the front page of your notes. I don't know how to take the antiderivative, so I don't know what big F is. So that's not going to help me. I don't have my calculator. So the best thing I can do is approximate it. What would you do to approximate it? Tell your neighbors. What would you do to approximate that? Okay, let's say I want you to use a right Riemann sum to approximate this. Let's say I want to use a right Riemann sum with 3 subintervals. Yep. You don't want to use 6. That'd be a lot of work. Because more would be a lot more. Okay, well, like, what do? Rojas. Oh, give somebody else a chance. Yes, what about it? Yo, make a table. Make a table. Start at the start, end at the end. You need 3 in between. So if you want 3 objects from 0 to 3, the width is all going to be 1. Now, instead of me giving you the y values, you need to just find the y values. Go ahead and find the y values, and then do a right Riemann sum. Please, a right Riemann sum with 3 subintervals. Okay, cool. Yeah, so I plug in 0, I get 0. I plug in 1, I get 2 over 2, which is 1. I plug in 2, I get 4 over 5. I'm going to put 0.8. I plug in 3, which is 6 over 10. I'm going to put 0.6. That'll be easier. All right. Go. Okay, go. You get it? 2.4? 12/5? Or 2.4? Cool? Now, do me a favor, if you have your calculator, go ahead and type this into your calculator. Like, type that into your calculator. You get 2.3. You were like pretty accurate with not that much work. You did not have to worry about a crazy antiderivative. We didn't even use that many points, and we're pretty accurate. Okay, the actual area is 2.3. But we can do better, and we will be expected to do better than just like, here's my value. We will be able to say, yo, here's my value, and I know that this approximation is over the actual. Do you remember the lesson back in the day, the tangent line approximation lesson, where Tucker dropped the F-bomb during class? It's my favorite moment of this class from the year. He's like, I'm looking at the effing graph. I was like, yeah, that was great. Okay, he could have had that same moment in this lesson, because we will be asked, hey, are your approximations over or under? So let's go to the next page. Let's talk about over and under approximations with area, but let's also remember what Tucker was so serious about. What was the important analysis that we had to make to determine if our tangent line approximations, remember, we used you gotta pump the brakes sometimes, man, where we were getting a y value on a line to approximate a y value on a curve. What was the key analysis that we had to do? Thanks, Nicholson. Concavity. We had to look at concavity, and we remember that if something was concave up and we drew a tangent line, our approximations were under, and if something was concave down and we drew a tangent line, our approximations are over. Now, these are y coordinates on line. This is not the situation here. The situation here is approximating an area, an accumulation. So like, at least we have that in our brain. Now we have three different graphs of f. They all have something in common, is that they're increasing. F is going up, the derivative is positive. Here there's no concavity. Here the second derivative is positive, it's concave up. Here is the second derivative being negative, f is concave down. Now let's think about a left Riemann sum. Now again, a left Riemann sum uses rectangles. You got your bases that are x's. You use the y's on the left of your interval. Tell me, over or under? Is a couple of them over, one of them under? Is this one under, that one over? Are they all over? Are they all under? Tell me. No, not right now. Not right now. You are here. Okay. All right. Over, under. Over, under. Over, under. Over, under. No. F times positive means the function's going up. No, that's a tangent line approximation. I want area. Here is the actual area right here. Here is the actual area right here. Here is the actual area right here. Is a left Riemann sum going to produce an under, an over, or I'm not sure, it depends on the situation, approximation? Tell your neighbors. Figure this out. Think about it. You're already checked out because you know you're not going to be here on Thursday. And that's soft. Tell me, a left Riemann sum. How do we create a left Riemann sum? Oh my gosh, this is so, hurts me. It hurts my feelings. You take a base I don't care how many bases you take. You take a height on the left of your base. Here is a height on the left of my base. That will be the height that I use over that base. You take another base. You will take your height over the base. And then you listen to Bodenstab tell you if your left Riemann sum for this first one will be under or over the actual area. Bodenstab, are you kidding me? Don't do this. Don't be this person. Don't be this student right now. Is this area of these rectangles less than or more than the overall area under that function F? Thank you. Don't you dare be like, I can't do it. Okay, great. One down. Two to go. Do it for these two, please.
They're all under.
They're all under, guys. It doesn't matter how many. You can use one. You can use one. The left y. Think about it. If your function is increasing, think. If your function is increasing and a left Riemann sum uses the points on the left, if your function is going up and I'm using the points on the left, I'm using the lowest point. This is also under. Oh, what about concave down? Well, a left Riemann sum uses the y on the left. Since it's an increasing function, I don't care if you use 2, if you use 4, if you use 8, or you just use 1, a left Riemann sum will use the lowest y values, and it'll be under.
He's only doing left Riemann.
I'm just doing left Riemann sum. Now, what do we notice? I don't care about concavity. Concavity has nothing to do with it. If F is going up, listen. Writer. If F is going up, a left Riemann sum will always be under, regardless of the concavity. What about a right Riemann sum? Over. Great, because we're going to use the highest y values on all of our intervals. Let's say we use one interval from 0 to b, and I use the height up here over my interval. Well, obviously, this is going to be more than the actual. Okay, now we're getting it. Great. All right, and if I use this one, oh, that's going to be more. So this is over, this is over, this is over. What about a trapezoidal Riemann sum? And again, because your function is increasing, we don't care about concavity. On a right Riemann sum, you're using the largest y value because your function is going up. What about a trapezoidal Riemann sum? Yeah, what about trapezoidal Riemann sum? The key is to how to connect, how to make the trapezoids. How to make the trapezoids is you take both y values and you connect them with a straight line. So since the first one is a straight line, guess what? We could use geometry to be dead on. Yeah, of course. This is going to be equal. But the second one and the third one is not equal. So tell your neighbors, second one or third one, over or under. All right, Frank. Second one, third one. Over, then under. So with the trapezoidal Riemann sum, concavity matters. Now, okay, we're going to go home and memorize that. Of course, you're not going to do that. Trapezoidal Riemann sum. You're not going to memorize this. You're just going to be able to draw a picture. You got to understand and remember one thing. One thing you're going to remember. It's not all about concavity. Your tangent line approximation, the y values on your line, it was about concavity. Here, not. It can be, but not always. It's about whether you're increasing or decreasing for left and right. It's about if we're concave up and concave down. What about midpoints? Don't worry about midpoints. Okay. Now, Verba asked the question, well, you don't care about accuracy. Why are we even doing this? What are we even doing here? How can I get better approximation? 6.5. No. Like, what? Smaller bases, more objects, right? More objects. More. Don't give me just 5 rectangles. Give me 10 rectangles. Okay, let's break this up and like break it into smaller, tinier rectangles. Great, with tinier bases, smaller sections. Boom. Okay, and this is going to be better than if I just use 3 rectangles. But instead of using 6, let's use 60. Instead of using 60, let's use 600. If you use 3 shapes, what's your width? If you use 6 shapes, what's your width if you're approximating something from 0 to 3? 6 shapes total, 6 subintervals. Tell your neighbors, if you are using 3 shapes from 0 to 3, what's the width of each of your shapes? 1. If you're using 6 shapes from 0 to 3, what's the width of each shape? More shapes goes to smaller width. Cool. Now, here comes the chicken egg situation. Okay? Ready? What we've been doing is summing up heights times bases. What's heights times bases? Area of a rectangle. Cool. Bases have been delta x's. Heights have just been y's that we've selected. Okay? Now, we don't really care about the start, but like you could start at a certain value and go to n objects. You guys are horrible at summation notation, but just this is the amount of objects that we're using. Cool. Now, more shapes, better approximation, more shapes, smaller bases. What would we want to do? Use an infinite amount of shapes. Now, do you guys remember how we've used infinity in the past? We've said, hey, don't really like plug it in, but think about approaching it. Think about approaching infinity. Think about like plugging in bigger and bigger and bigger values. What did we use way back at the beginning of this class? I talked about approaching infinity. Limit. Hooray. Okay, now, hold on. That's an infinity. Infinite amount of objects. Okay, better and better approximation. What happens to the width of all my objects? Gets smaller and smaller and smaller and smaller and smaller. It's going to approach 0. It's not going to be like an overall change in x. It turns into a very small change in x. Where have our y's come from? Our y's have come from function values. And what have we been doing? accumulating. Turns out, guys, an accumulation is an infinite sum. It is an antiderivative. It is all of that and more. Turns out when we've been writing this is not good. This is not correct. This is not an area because it's one dimension. If you just add up y's, you're just adding up y's. You're going to get infinity. You won't get a number, and that you will figure out more if you look at BC. This is bad. You want two dimensions to get area. You need height times basis. dx is required. dx is why, if this was a derivative, we get meters per second times the infinite seconds in which we're at that meters per second, and we get meters, or displacement. We've been doing kind of Riemann sums all along, even if you haven't seen it. But if that doesn't make sense to you, honestly, it doesn't matter. Because what we're going to do is review Unit 7 and Unit 8, okay? We're just going to review stuff that we've already done. It's going to look a little different, but we got to just understand what we've been doing all along. We hope you understand the conceptual theoretical parts, but in the long run, we don't. Okay, so, guys, your test, your Unit 9 test, will be one free response question like Unit 7, but you have to use Riemann sum. It will be one rate in, rate out question, but with Riemann sum. And then it'll be some multiple choice problems. Okay? Multiple choice is back, all right. Yeah. All right. So here's the situation. This is Unit 7. This is motion. A person is doing gases on a basketball court along the sideline. Their velocities are being tracked by a specialized GPS they are wearing. Here are some velocities tracked in meters per second for t seconds. Boom. Cool? Positive velocity is positions increasing. Negative velocity is positions decreasing. Approximate the integral from 0 to 6 of v using a trapezoidal Riemann sum with some intervals indicated by the data. Now, here's what we got to get through to you. The Riemann sum is 1 point. Getting that value, 1 point. Congrats if you get that point. But there's 2 more points in this problem. Given v is increasing and then decreasing at a decreasing rate, use units to explain the meaning of your answer and if it's an over-under approximation. 2 more points. It's not just about getting answers. It's understanding what they mean. So, first things first, pay attention to the fact that we're only going from 0 to 6. Okay. Can you guys do a trapezoidal Riemann sum from 0 to 6? Go. We have enough time to get through this question. Go.
Oh, yeah. I had it on.
No. I said, it doesn't matter. Now you can do this problem. I hope you were paying attention while you were waiting. Great.
This stuff makes more sense than the last one.
Oh, you didn't pay attention. All right, we get 24. 24. Great, you got a point for 24. Now, it is easier to use the formula than to do the visualization. Let me help those of you not jumping in. 1/2 base of 2, height of 1 plus 6. This is 7. You can use your calculator for this. Let's just get the answers. The next one is a base of 3, height of 6 and 4. So this is like 1.5 times 10, which is 15. Again, 1/2 base of 3, height of 6 and 4. Then the last one is 5 to 6, base of 1, height of 4 and 0. It actually is just a rectangle, 1/2 base of 1, height of 4, which is 2. So we get 15 plus 7 plus 2. What happened? Which is 24. Cool. 1/2 base of 1, heights of 4, and 0. All right, great. You just got 1 point out of the 3 possible. Now, telling your neighbors, what does this mean with units? Give me the units for this number. Units count now. Units count. What are the units and what is the meaning? Go. Tell your neighbors, what's the units? What's the meaning? They've not done 24 gases. That's a lot. Ready? Here's the next thing you need to help with. F prime, F double prime. X, V, A. What did you do? You accumulated V. You could take an antiderivative if you wanted to. What do you get when you use an integral of V? You go backwards. You get a position. Meters. Meters per second. Meters per second squared. It's always been. It's a position. It's a change of position. It's a change of a change. This is displacement. This is meters. This is a change in position. This is the idea of your velocity being positive. Means your position is increasing. The area under your velocity tells us how much the position is increasing. You can look at x of b minus x of a, and you would get this minus this is that, or that plus that is that, right? It's the whole beautiful connection. So that is a displacement. That's in meters. That's another way to think about how do we get meters. We summed up your velocity times your time. You took velocity times time. Velocity times time, meters. It's another way to kind of understand what's going on. Is it over or under? And why? It is increasing and then decreasing, but its rate is decreasing. What does that mean? My velocity is concave down. If your velocity is concave down and use trapezoids, guess what? Under. Concavity matters for trapezoids. Concavity does not matter for left and right. Okay, cool. So like, the key to this lesson is like, a Riemann sum's easy. You all should be like, yeah, Riemann sums are easy. But remembering, like, reasoning and meanings behind what we've been doing, that's important. So, here's your next question. Use a left Riemann sum with subintervals indicated by a data to approximate the integral from 2 to 9. Pay attention that we're just starting at 2 and we're going to 9. We're not going from the beginning to the end. 2 to 9 of v times of 7. Give me units. Tell me the meaning of my answer. Tell me if my answer is over or under. This is a free response question. This is free response practice right now. The integral is 18. So the answer is 18 over 7. See if you can get that. So it's 18.7. 18/7. Okay, I'm going from 2 to 9. I got a base of 3, height 6. Base of 1, height 4. Base of 1, height 0. Base of 1, height -1. Base of 1, height -3. So I got 18 plus 4 is 22, plus 0, minus 1, which is 21, minus 3, which is 18. Okay, are we cool getting 18? If you're not cool, you got to be able to get it. Let's now talk about the meaning. Go. What is the meaning of the answer and what's the correct units? Go. What is it? Yeah, but give me like the... Good. Ready, guys? Here's the key. You're not used to seeing that 1/7 in front. You're used to seeing an integral divided by 7. Yeah, remember that? Remember that? Adding up all our velocities and dividing by the interval. Now, what we get here is meters per second over an interval of seconds, which is in meters, but that is divided by an interval of seconds. This is my average velocity. Remember, add up all of our velocities divided by the interval. It's an average. This is not meters. This is meters per second because you divided it by 7. This is meters. This is the interval of seconds. Meters per second. It's not about getting the value, guys. It's about remembering the conceptual understanding of things. That will help you. Over or under? You see Ryder, he's like, dude, guys, it's obviously... Yeah, it's not under, it's over. The function is decreasing. If you have a decreasing function and you're using a left height, the left height will be over. Yeah. Function is decreasing. I'm using the heights on my left. I'm over. You got to figure this out. Use a midpoint sum to approximate this integral. Two intervals. Use a midpoint Riemann sum with 2 subintervals. Just area approximation. It's just like we're using geometry, we're approximating area. Can't wait. Can't wait to grade it. Good. Okay. Now, 7. Where are we going? 5 to 9? 5 to 7. I'm using 0. 7 to 9, I'm not using 3. I'm not using -3. I'm using +3 because it tells me to approximate the integral, the absolute value of velocity. So this is a big fat 0, but this should be a big fat 6. Now what is the unit and what is the meaning? What are the units? What is the meaning? Not correct.
It's meters, but it's absolute value of meters.
It's +6 meters. It is distance traveled. This is why we took the absolute value of velocity, so we didn't have to worry about negative displacement moving left. Wait, we're not done yet. The next question is super important. Approximate the acceleration at t equals 1. This is just as important as all the others. What's the relationship between acceleration and velocity? The derivative of velocity is acceleration. The slope of velocity is acceleration. At 1 is between 0 and 2. Could you find the slope of velocity between 0 and 2? Yes, 6 minus 1 is 5. 5 divided by 2. You will be using your table to sometimes
I have that homework from today. Let's see that quiz we did.
Cool.
That I was there for.
Cool.
Where do I put it? Right here?
Yep.
Sweet. Thank you, Mr. Leslie.
Later.